what we've been doing. We were in okay, sorry about that. Yeah, we've been doing the synthesis of combination circuits. So that was in general we have seen what the synthesis is, and then in the second step we said in order to increase not increase, just the opposite, reduce the cost of a synthesis, we've got to use a method. For this method, we've got to define a minimal function. So we define that minimal function in this frame. And then we said, so that was this definition of minimal function. At the end of this definition, we said we are going to find the prime implicants and then the essential prime implicants and then find the minimal function. So how we are going to find this prime implicants and that has essential prime implicants is related with this frame. So we will be examining this frame now. In this frame, definition of the minimal function has got two parts. One of them is and or type of minimal function related with the first canonical expansion, or sum of products form minimal function. So this is one thing that we got to know. The second step is definition of minimal function for product of sums form. That means or and form realization. So in this frame we will be examining sum of products form minimal function. So how we are going to find a minimal function for a given circuit, for a given function, to find the minimal function which is in this form, sum of products form. So let's go in and examine this now. So we're going to come out of here, take this off, and put this on open board, and then OBS, open board. So that's the one. Okay, here we are. So what we know in this before this video, we learned that we need to find, in order to find a minimal function, we've got to find out prime implicants. Prime implicants, these are the product terms which has got minimum number of variables in it. So the first step is to find these prime implicants, and then among these prime implicants we are going to find the essential prime implicants, prime implicants, and then we are going to put all the minimal functions must have these essential prime implicants in, and then underneath we are going to find minimal number of prime implicants. When we add these prime implicants to our essential prime implicants, then we are going to get the minimal function, that minimal function. So we're going to find all the prime implicants. Among those we are going to find the essential prime implicants, and we are going to add minimal number of prime implicants to the essential prime implicants in order to find the minimal function. This is the rule that we have already found. Now how we are going to find it is in this video now. There are three steps. So we know that finding the prime implicants, we're going to use this elimination method. Elimination method is a product term which has got one variable is changing, the other variables are not changing. If there are two product terms like that, so make me a bit, sorry, to correct that, a prime. One variable is changing, that's one variable. The others variable are not changing. This, we are going to end up with this a. That means instead of, this is represent an AND gate, this represent another AND gate. So if you've got two product terms like that, we are going to use only one AND gate, not two, but just one. And one variable is going to disappear. That means the AND gate fan in is going to be the same as the number of variables that we see in this capital A. In here, this AND gate has got the number of variables in A plus 1. This is also fan in the number of variables in A plus another variable, gives you the fan in of these AND gates. Clear this now. So one way, the easiest way of finding all these prime implicants or applying this elimination operation is grouping the true minterms of a given function. I'm going to explain it on a given function. So assume that this is the function given to you. So we're going to find the minimal function for this given function. How I could find out the minimal operation cases for this function, I'm going to group these true minterms as follows. I am going to, each number here written as binary is this. So each one of these rows represent a true minterm. For example, this is, let me write this representing x1 prime, x2 prime, x3 prime, x4 prime. And this another one here, let me write it in different colors. x1 prime, x2 prime, x3 prime. Since the last one it has value 1, so x4. So if you look at these two product terms, it is two product terms which is good for variable elimination operation. Why is that? Because I can consider this is an A, this is a capital A, and one variable is changing. This variable is going to disappear, and what's going to left is going to be x1 prime, x2 prime, x3 prime. This is one variable elimination operation. So the easiest way to find all these operations is to group these true minterms. How we are grouping it? Put all the true minterms, which includes only which includes no ones in it. So here you are, 0 true minterm, which includes 0, 1 in it. This second group of minterms in which we've got only one value in it. Here you are, 1, 2, 3. Each one of them has got just 1 in it. Just one in it. In this third group, we group the minterms 5, 9, and 10. These true minterms has got only 2 ones in it. For example, 1, 2 for the 5, for 9, 1, 2, for 10, 1, 2. So this 5, 9, and 10 true minterms has got only 2 ones in it. The fourth group, the true minterms has got only 3 ones in it, and the last one has got 4 ones in it. So when we group them like that, we can conclude this. we can say that any operation like that, variable elimination operation like that, is possible between a neighbor group minterms. That means there could be an operation like that between 0 and 1, but there wouldn't be an operation like that between first group and the third group, non-neighbor groups. Example, so this one is x1 prime, x2 prime, x3 prime, x4 prime. That's 0 minterm. If you choose that 5 is x1, x2 prime, x2 prime, make x1 prime, x2, x3 prime, x4. So that's 5. That's 0, 1, 0, 1. So that is 0, 0, 0, 0. So these two product terms cannot make a elimination operation. Why is that? Because two variable is changing, isn't it? Here x2 is changing, in here x2 prime, in here x2. x4 is also changing. Not only one variable, but two variables is changing. Therefore, these two product terms cannot make an elimination operation. So conclusion is that elimination operation is possible between the neighbor groups minterms. So that means you are not going to compare this true minterm with group 3, group 4, group 5, sorry. So this group minterm, only this group can make an elimination operation, not this group, not this group, not this group. You don't have to do comparison for those. For example, for this group, any one of the true minterm here should be compared with the true minterm in the neighbor groups. So that means 1, 5, 1, 9, 1, 10. 2, 5, 2, 9, 2, 10, 8, 5, 8, 9, 8, 10. Not second group and the third group, because non-neighbor groups true minterms cannot make an elimination operation like that. Therefore, we are saying that this grouping helps me which comparisons between the product terms I will be doing. This tells me. So if we apply this now, let me clear this area once more and go one step further. Here are, if I compare 0 with 1, I end up with this one. Why is that? Because the only x4 is changing, so there's a dash for this position. And the others are not changing. These variables are not changing, whether it is 0 minterm or the 1 minterm. So I keep all these positions 0, 0, 0. The changing variable position, I put a dash. So at the end of this operation, 0, 1 true minterms elimination operation, I end up with this result. This result means, so this is, directly I can write it x1 prime, x2 prime, x3 prime. That's the one already we have found. So if we compare this 0 and 2, it's going to be this one. Why is that? 0 and 2, you see, only the x3 is changing. The others are the same, and the values are 0. So because of that x3 is changing, I put a dash for this position and keep the other unchanged values as they are, 0, 0, dash 0. So the corresponding, after the elimination, the product term to this one is x1 prime, x2 prime, no x3, x4 prime. So after the elimination, what I see is this. So you can continue like that, and you're going to end up with this result. So that means you compare 0, 1, 0, 2, 0, 8, And then don't compare 0, 5, 0, 9, 0, 10 and the other non-neighbor group minterms. So the second, you're going to compare 1, 5, 1, 9, 1, 10, 2, 5, 2, 9, 2, 10, 8, 5, 8, 9, 8, 10. Not this group true minterms and this group true minterms are not going to be compared at all because they are non-neighbor true minterms. Okay, so if you do this operation or after the end of the comparisons, so that means 7, 15 and 13, 15. Let's say, let me show you 13, 15 as an example. 13, 15, where is that? So the 5 is missing here. 13, 15, x3 position variable is going to disappear, so it's going to be a dash in that position. For the other variables, the values are not, the values for all of these variables, they are 1, so put that 1, 1, dash 1. So that is the elimination operation between 13 and 15. You end up with this line. So in this group now, how we are going to continue? We are going to continue once more by regrouping the resulting ones. How I regroup them? If you look at the first group, you've got 0 ones included product terms, only 1 included product terms, only 2 ones included product terms, one group, only 3 ones included product groups, product minterms, product terms in the last group. So when you do this grouping, the rule of the elimination operation possible is this. If the dash position, we are going to compare the product terms between the neighbor groups. That's first thing. The second condition is this. The dash positions must be the same. For example, this dash position and this position is the same, isn't it? Because X4 position has got dash in these two neighbor group true minterms. So let me write that. X1, X2, X3, prime, prime, prime. Because of dash, I didn't write anything. And for the other, this one, for 8, 9, operation result is X1, X2, X3 prime, X2 prime. Because X2 value is 0, X3 value is also 0. So look at this two now. This tells me another elimination operation. Why is that? This X2 prime and X3 prime common in both of these product terms. Therefore, X2 prime, X3 prime, in parentheses, X1 prime, X1. So this gives me 1, another variable elimination, that is. So by comparing two product terms in neighbor groups, I have found an elimination operation. But it doesn't mean that all same dash position included product terms is going to have a elimination operation. So I can show you this here. If you look at this too, dash position, they are in neighbor groups. Dash positions are the same, but all the variable values are changing. There should be only one variable value changing. So this 2, for example, is not good for applying the elimination operation. So if you say that, what does this mean, an elimination operation after this group and after that group? And this group and this group, sorry. So what happens here? 0, 1 and 8, 9. 0.0189. After the elimination, I have got this. Here you are, x2 prime, x3 prime. So we are going to compare now between these, in this second step, neighbor group product terms, find out the elimination operations, and continue until the end, until the comparison of the neighbor groups products. So you're going to end up with this. This table here is the same as this. So this one shows how to change from this one, and this one shows how to change this one to third one. That's why we repeat it twice here. So when you end up with, that is what we end up with. Now, let's try to continue. So we're going to make group once more. In this first group, we've got product terms which includes 0 ones in it. This second group has got only one included product term, only 1 included product term. So I'm going to compare the neighbor groups, and the dash positions must be the same as well. So in here, for example, this product term and this product term does not give me any elimination operation because the dash positions are different. This one and this one, dash positions are different, so no elimination. So this one and this one, once again, the dash positions are different, therefore there is no elimination operation like that. I do not compare non-neighbor groups, this one and this one. Okay. So that means you cannot go any further because there is no minimal elimination operation like that when you compare the neighbor groups in this step. So then you're going to stop. When you stop, all these rows tells me the prime implicants. This is in Turkish, but it is in English. Prime implicants these are. Why I call this prime implicants? Because you cannot go to the elimination. So you cannot reduce the number of variables in these product variables. So that is the definition of minimal function. We said minimal function is going to have product terms which has got minimal number of variables in it. If I cannot eliminate any variable here, then it is a prime implicant. So these are the prime implicants that I found. But we've got to pay attention in here. If you look at all these prime implicants includes these true mean terms. So these true mean terms, all of them is also in this given function, isn't it? So if you, at the end of the step 2, if you write the prime implicants, which does not cover some of the true mean terms of this function at that stage, then that means these true mean terms are covered in the previous step. So you've got to find out this previous step product term, and this product term is also prime implicant. Why I said that? Because when you consider the prime implicants, these prime implicants must include all the true mean terms of the given function. If some of them missing, means you couldn't find the all prime implicants. That is the reason of it. Let's go a bit further now. So we found the prime implicants. How we are going to find the essential prime implicant? We said essential prime implicants must be in the minimal functions. Minimal functions includes essential prime implicants. That is guarantee. So in the previous stage, I found prime implicants. How I'm going to find the essential prime implicants? We are going to make an essential prime implicant table. This is called essential prime implicant. Essential prime implicant table. How we write this table? You see the rows here. We write the prime implicants that we found in the previous stage. And these are the true minterms. True minterms. These are the prime implicants. So these are the prime implicants. So this prime implicant, which is x2 prime, x3 prime, covers which true minterms? 0, 1, 8, 9. So which is included here? 0, 1, 8, 9. So I put mark to 0 position, 1 position, 8 and 9 position. Meaning is this. This product term covers 0, 1, 8, 9 true minterms. So easy to mark them. So if you do all these marking here, and then we're going to go up one further step. What is this step? If there is a column in which there is only one mark in it, then put a circle around it. So here you are. So in this column here, we've got only one mark. We are going to put that mark in a circle. The meaning is this. The corresponding row to this circled mark is essential prime implicant. So these are essential prime implicant, but this one here, essential prime implicant. Why is that? The meaning is this. This prime implicant, this true minterm 2, is only covered by this prime implicant. There is no any other prime implicant which covers this true minterm 2. Therefore, it is an essential prime implicant. So if you remember, the essential prime implicant was this. Essential prime implicant is a prime implicant which covers one true minterms which is not covered by any other prime implicants. So if there is only one circled mark, that means there is no other mark around. So that means this true minterms is not covered by any other prime implicants. Therefore, the corresponding row is the essential prime implicant. So if you look at this column 7, so there is only one mark here. The corresponding, this line is also essential prime implicant. So if you look at this column 10, so we put in a circle, the corresponding row, it was already an essential prime implicant. Now it is now duplicated essential prime implicant. Why is that? Because of that 2, it is essential prime implicant. Also, because of that 10, it is an essential prime implicant. So if you look at this, because of that 7, this prime implicant is essential prime implicant. Because of this column here, because of this column has got one circled mark here, the corresponding row is the essential prime implicant because of that 15 true minterm. Because of that. Okay. So in that prime implicant table, I found essential prime implicants. So this essential prime implicant, one of them is this, the other one is this. We said we must have these essential prime implicants in the minimal function. So this f minimal function has got this. Now the further step tells us we are going to write minimal number of prime implicants next to these essential prime implicants. So how we are going to make that decision? Easy. Look at this table here. When we consider these essential prime implicants that we said must be included in the minimal function, so this marked true min terms are covered. So this one, 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 and this one. These true min terms means 0, 2, 5, 7, 8, 10, 13, 15. True min terms are covered by these essential prime implicants. That means by this. So what is left, make it different color. This 0 true min term and this 9 true min terms are not covered by these essential prime implicants. Okay. So what it means, without considering this last one here, this function, this minimal function, does not covered by our function. It is not equivalent. To make it equivalent, we've got to put minimal number of prime implicants next to these essential prime implicants in order to cover this 1 and 9 true min terms. So how I'm going to make the decision, look at these columns here. So 1 and 9 true min terms are included in this prime implicant. So if I put this prime implicant next to the essential prime implicants, so in here it is made, let me clear this. So this red. So I wrote two minimal functions here. These are essential prime implicants. This is the essential prime implicants. Now, because of that blue one here, I put next to this, that's prime implicant. These two is essential prime implicant. This prime implicants, when I add up, I consider true min term 1 and 9 as well. So if you consider this minimal function altogether, this minimal function covers all the true min terms for the given circuit, for the given function. Given function was this 0, 1, 2, 5, 7, 8, 9, 10, 13, 15. Now I am saying this minimum function now covers all these true min terms. So that means they are equivalent to each other. So there is another the minimal function here. That was one of them, this one. This one is the another one of them. Let's say this one and this is 2. So min term 1 is the other one. How I found that? So if you look at this here now, these 1 and 9 true min terms are not included in the essential prime implicant. But if you look at 1, another color, make it green. So look at this one. Here you are, this one, green I said, but it didn't become green. So I'm clear. Okay. So this one and this 9 is included in this prime implicant. So that means if I consider this prime implicant instead of this blue one, I can make another minimal function. So that is this one. Conclusion is this. For this given circuit, there are two minimal functions. One of them is this one. The other one is this one. In both minimal functions, essential prime implicants are the same. These red ones. The additional prime implicants are changing. This green one and this blue one here. Okay. So how we are finding the minimal functions? We already said that minimal functions are not unique. There could be more than one minimal function for a given function. Let's compare the result now. That's the given function. This given function, if you write the first canonical form, or sum of products form, you're going to end up with this, because you've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We've got 10 true minterms. Each minterm corresponds to an AND gate. So AND gate 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Fan-in of these AND gates is going to be 4, because we've got 4 variable function. This function has got 4 independent variables. So fan-in of the AND gates, is 4. Fan-in of, there is only one OR gate, so this comes from the sum, from sum of products. So this sum is that OR gate. This OR gate fan-in is the same as the number of AND gates, because all the AND gates outputs are connected to the OR gate. So fan-in is 10. So conclusion, if you use first canonical form, the design has got 10 AND gates with 4 fan-ins each, and 1 OR gate with 10 fan-in. Now these two are the minimal function 1, minimal function 2. So if you write these elements in here, so we've got 3 AND gates, not 10 but 3, with 2 fan-in, not 4, just 2 fan-in. So OR gate, once again, just one OR gate, but with 3 fan-in, not 10. So you're going to compare this 10, this 3, and you're going to compare this 10, this 3, make it different color, and this 4, this 2. So this one is much better, you can see it. So we are saying now the efficiency and effectiveness has been increased. Why is that? So for example, you've got 10 AND gates you've got here. So 4 input AND gates included one integrated circuit. In one integrated circuit, you've got 2 of them, so you're going to have 5 integrated circuit in this case. But in here, only one integrated gate for the AND gates. So 5 reduced to 1. So that means the cost has been reduced drastically. Apart from that, the power consumption is going to be much less for the minimal function realization, because the number of integrated circuits increase means the power that you're going to consume for each integrated circuit is going to be reduced 5 times in this case. So that means for a long time you are consuming less electrical energy to do the same job. That's why the efficiency has been reduced. Because the cost reduced, it is a more effective one as well. It is a good design. Now, what has changed? What has not been changed? We can say that in this group, since it is sum of products form, so this is AND OR form, and this is also AND OR form. This is 2 level, and this is also 2 level. These two has not changed. What has changed? The number of elements has changed. The fan-in values also change. So that is the benefit of using this method. This method is called Quinn-McCluskey method and gives you minimal cost function under the condition that 2-level realization and OR type elements included realization. For example, the XOR type element included realization is not here. You've got to use another method for that. You might ask one more question saying that why we have found all the minimal functions. Is there any benefit for that? Yes, there is a benefit for it. How we can do it? So I'll show you. If you are going to design a circuit which has got 2 outputs in it, one of them is F, the other one is G. Assume that you found the G minimal function in order to reduce the cost of this circuit that you're going to design. G minimal function, assume that you've got one product term which is x2 prime and x3 prime in it. So if you find all the minimal functions for the F, for example in this case these two, since you have got in your minimal functions for the G function this, for the F minimal functions you're going to choose this one, not this one. Why is that? Because if you choose this minimal function, you're going to have this gate in this minimal function, also in this G minimal function. So that means you can share this AND gate for the design of F and at the same time for the G as well. Therefore, we need to find all the minimal functions for a given function. If we are going to do a design which has got more than 1 outputs, then that is going to be beneficial. If it is only just one, the cost of this minimal function and this minimal function is the same. Why is that? This one has got 3 AND gates, this one has got 3 AND gates, this one, all the fan-ins of the AND gates is 2. For this case, it is 2 as well. So this OR gate just 1, and the fan-in for these AND gates are the same. So the cost of this and this the same. Why we are considering the cost of a circuit? We do not count these prime, not gates. Why we do not count them? Because this is an independent variable. The prime of an independent variable could be available somewhere in the whole circuit, somewhere. So you can use the output of this NOT gate. Therefore, we don't count this independent variable related NOT gates. We don't count them. So that's the end of this video then.